This lecture explains what stellar spectroscopy is, and how it was developed historically. Some of the view graphs were borrowed from presentations found online. The learning goals of this lecture are to know the basic spectral luminosity classes, and to explain how human computers, women, working for Harvard contributed to stellar spectral classification. Spectral classification is the process of organizing stars into categories based on the features in their spectra. It uses several different techniques such as looking at the strength of the absorption lines, looking at the peak of the blackbody curve, and by the temperature and luminosity of the stars. Much of the work in classifying and explaining stellar spectra and brightness was done by women at Harvard around the turn of the century. Single-handedly, Annie Jumpcannon classified more than 250,000 stellar spectra. Henrietta Leavitt classified stars by their spectra as O, B, A, F, G, K, and M spectral types. Some stars she looked at seemed to pulse with a variable brightness. She discovered the relation between luminosity and period of Cepheid variable stars. This relationship enabled astronomers to measure the distance to galaxies outside the solar system. In the 1800s, researchers were making connections to explain their data. They could only measure the light from distant stars, and had no way to directly measure luminosity, mass, or temperature. They observed the strength of hydrogen absorption lines and the blackbody curve in laboratory experiments. They developed a theory about stellar evolution that predicts how to determine the values of temperature, luminosity, and mass. One of the Harvard researchers includes Cecilia Payne, a British-American astronomer and astrophysicist who, in 1925, proposed in her PhD thesis an explanation for the composition of stars in terms of the relative abundances of hydrogen and helium. Each star is born with a specific mass. This mass is the main factor in determining the star's brightness, temperature, expected lifetime, type of death, and spectra. Stars are classified according to their spectra. Astronomers discovered that large numbers of stars exhibit a small number of distinct patterns in their spectral features. Spectral lines are caused by different elements present in a star. The overall spectrum is strongly related to the surface temperature of the star. Stars are then categorized into classes distinguished by the strength of the spectral lines and their shape. There are 7 classes of stars, O, B, A, F, G, K, and M. From O to M, stars decrease in temperature and mass, but increase in lifetime. These are 2 of many mnemonic devices students and astronomers use to remember the proper order of stellar classification, from the hottest blue stars, O-type, to the coldest red stars, M-type. O stars are the most massive, hottest, and brightest stars. These rock stars of the universe live fast, die young, and leave a spectacular-looking corpse when they supernova. B stars are very hot and bright, and large, and massive. They are very rare, and less than 1% of the main sequence stars are B stars. Rigel and Spica are easy to find in the night sky. These massive stars are short-lived compared to most main sequence stars. Most of the bright, visible stars in the night sky are A stars. Vega and Sirius are famous and easy to find. A stars are hot and short-lived. F stars are slightly bigger and hotter than the Sun. They have a slightly shorter lifespan than the Sun. Since they are similar, researchers look for extrasolar planets around them. Scientists hypothesize that it takes millions of years for life to evolve, so F, G, and K-type stars live long enough for there to be hope to find life there. Our own Sun is a very average G star. Like our Sun, G stars have weak hydrogen lines, and both neutral and ionized metals in the outer atmosphere. Arcturus and Aldebaran are two K stars that are fairly easy to find in the night sky. K stars are smaller and cooler than the Sun. They will live longer than the Sun. For these reasons, they are considered candidate stars in the search for extrasolar planets. Most stars are red stars. The color and brightness of Antares is very close to the color and brightness of Mars. Sometimes they are close in the sky, and you'll need a finder chart or some software to identify them. Main sequence M stars are the longest living main sequence stars. The spectra of stars depends on both their chemical composition and their temperature. The temperature determines which series of lines will be present if the chemical is present. Figure 10.12 shows the spectra of stars with different types ranging from hot blue O stars to cool red M stars. In summary, in the 1800s, researchers at Harvard developed a taxonomy of stars based on their spectra, temperature, and to a smaller extent, strength of spectral lines, are the basis for the stellar luminosity classification system. A recommended book for general audience is The Glass Universe by Dava Sobel. This excellent and entertaining book is historically accurate and detailed, where author Dava Sobel explains how it happened, neither sanitizing nor embellishing the past.